Good morning, everyone. You're still sleepy. How was it yesterday? Good. Wonderful. Well, today going to be even better. Yeah, Jacqueline has organized a lot of things for us this afternoon. So we will have lunch here, and then we will get ready to move. What time we're moving? 2 o'clock. Yeah. So we're going to try to keep it on time today morning, so we can have time in the afternoon. So, well, Bruno volunteered to to substitute. So, Bruno, are you ready? Because we are ready over there. We just need to connect you.
Yes, I need to connect, right?
Yeah, yeah. Still few people are arriving. So, how many of you are staying for Thursday? Good. Because there is a tradition to organize a video session in the evening. It's like completely relaxed session. It's usually with wine and cheese and and we are wondering whether we will do it tonight after returning from Medina or on Thursday. What time we were coming back on Thursday? 5. Yeah, I think. Yeah, I think Thursday. I mean, if you're staying Thursday night, that would be good. And the way it works is that we
Tonight or Wednesday? Because
yeah.
Thursday we have dinner.
Well, you have also another appointment. Okay. All right. Anyway, no, but it's good to know. I mean, we're going to schedule it, and the way it works is we have an organizer in the back who's going to take your names and short title of your presentation. The videos will be like 2-3 minutes. I mean, maximum 2.5 minutes presentation. So just like a hot, new, latest development in your research or around your lab. And then it will be like about an hour. We might have it tonight. We will decide later, depending on the time we're coming back. So we'll see, or tomorrow. The problem is also tomorrow we have some activity, so it will be late. So we'll.
Jacqueline, which night will be back earlier? Tonight or tomorrow? Thursday.
Yeah, Thursday at 5, so it might work at 5.
Yeah, okay, sure.
Yeah, are you ready?
Yes, I'm almost connected.
Yeah. I think we will discuss a little later and see how we can do this. Okay. We need to get people in the.
Yes, I'm connecting now. Takes a while, but yeah. Okay. Yes.
You're connected. Okay, so Bruno will introduce the first.
Okay. Can you have admitted me? Okay. Okay. Good morning. This is again Bruno Siciliano, co-chair of this symposium, and this is session number 5. Should have been chaired by Antonio Bicchi from University of Pisa and IIT, but unfortunately he had some health problems in the family, so he couldn't join us. So I am just sitting in and replacing him for this session on perception. And this is the session with the largest number of presentations in person, which is good, 5 out of 6. And the first one is by colleagues and friends from Freiburg. is Oyer Mess and Wolfram Burgert, and Oyer will be presenting a paper titled Composing Pick and Place Tasks by Grounding Language. Please.
Thank you for the nice introduction. Hi, my name is Oyer, and as Bruno said, welcome to my presentation on composing pick and place tasks by grounding language. So, robots coexisting with humans in their environment must learn to relate human language to their perceptions and actions in order to be useful in a range of daily tasks. Natural language provides a rich and intuitive way for humans and robots to interact due to the possibility of referring to abstract concepts. In this work, we aim to develop an approach that enables robots to solve manipulation tasks by understanding a series of unconstrained language expressions characterizing pick-and-place commands. As such compositions can lead to desirable high-level behaviors such as tidying up or setting a table. So let's start with how to pick an object based on language instructions. To do so, the robot has to locate unconstrained object categories based on arbitrary natural language expressions, known as referring expression comprehension. In other words, the robot needs to ground the referred objects from language in its world model. This is very challenging because, for example, here the robot needs to understand that there are 3 candidate objects that could potentially fit with this user query of the blue bowl and ask the user to disambiguate this. Our approach infers objects and their relationships from input images and language expressions and can place objects in accordance with the spatial relations expressed by the user. Unlike previous approaches, we consider grounding not only for the picking, but also for the placement of everyday objects in language, from language. Our grounding network processes the input sentences and visual object candidates detected with mask RCNN and performs referential expression comprehension. Additionally, it generates referential expressions for each object candidate to disambiguate unclear instructions, as you can see over here. Once the reference object of a relative placement instruction has been identified, a second network over here predicts placing locations for a set of spatial relations. Okay, so given an input image and an expression, the target object selection is formulated as a task to find the best bounding box from a set of candidate bounding boxes, candidate boxes. In our approach, candidate regions are encoded by a neural network based on the MATNet architecture, consisting of 3 modular grounding components related to subject appearance, location, and relationship to other objects. Each visual module computes scores for each candidate object by calculating the cosine similarity between the vector representation of the instruction and that of the candidate image regions. During training, we sample triplets consisting of a positive match and 2 random negative samples with incorrect sentences or objects to apply a hinge loss. In order to detect if an instruction is ambiguous, we leverage the max margin loss of the comprehension model. Concretely, during the training, the max margin loss aims to guarantee that every correct pair of object and sentences has a higher score than a margin M1 than any other pair with the incorrect object or sentence. Therefore, if at test time there are more than 1 objects within the threshold, we consider them potential targets. Inspired by recent advances in image captioning, we incorporate a LSTM-based captioning module to our grounding network that allows the robot to describe each detected object with a natural language description. Our referring expression generation module is jointly trained with our grounding network and shares the features used in the 3 modules related to subject appearance, location, and relationship to other objects. This module, this captioning module, is trained to generate the sentences by minimizing the negative log likelihood of the visual representation of the target object. VI in this case is the visual representation of the target object. And however, we don't want to only generate captions, but we want to generate referring expression, right? So we don't want to describe this is a banana, but we want to be able to say this is the left banana or the middle banana, so that this description is unambiguous. And in order to generate discriminative sentences, we use a maximum mutual information constraint that encourages the generated expression to describe the target object better than other objects within the image. This is the second gloss over here. So concretely, given a positive match, we sample a negative one where we have some other negative object and follow and optimize again a max margin loss. We compare our grounding network's ability to comprehend and generate referring expressions against several strong baselines in the RevCoco dataset, and we observed that by jointly training the comprehension and generation modules, they regularize each other and improve their respective performances. For each candidate, we generate multiple self-referential expressions via beam search and use the comprehension modules to re-rank these expressions and select the least ambiguous one. And here you can see some of the referring expressions generated by our network, and you can see with beam search, and you can see that most of them are useful, like here the tall bottle or the bottle in the back, the green mark, the top bowl, the right bottle, but others are not that good, like here this is a tennis ball, but it says the right fruit. Yeah. Okay, so once an object has been correctly identified and picked, we need to ground the spatial relations. Spatial relations as most object placement commands are relative to another. But how do we define an object placing location? Usually from spatial relations alone, it's not possible to know at which exact location a user would like to place an object in relation to another. In this example, all this region here, for example, could be a possible right of the box. Thus, ideally, for a given relational instruction, we would like to be able to have a pixel-wise probability distribution from which we could sample an object placing location. However, one of the key challenges to estimate such a pixel-wise ground truth distribution is the lack of ground truth data. This originates from the inherent uncertainty on modeling such ground truth distributions without using heuristics. So we know that classifying relations between two objects can be efficiently learned with supervised learning. However, if we want to place an object in relation to another, we do not have both objects in the scene, right? So this is the challenge or the problem. So we need to imagine what spatial relation both objects would form if the object to be placed was placed at different locations. So for example, given this bowl over here, what relation would be formed if we place this sponge over here, or if we place it on top of it, or at different positions? Naively pasting object masks in images or in painting is computationally expensive and requires segmentation masks. So to sidestep this issue, we propose implanting high-level features of an object to trick a classifier into classifying hallucinated scenes. In this case, for example, we could ask the network what relation an imaginary object would form if we place it here in front of the orange cap, for example, and then this classifier would say that this is in front of the orange cap. So we make use of this technique to develop our full approach for generating spatial distributions for an image and candidate object. And this is based on our prior work we presented last year at ICRA. So our spatial RelNet network processes the input RGB image and the object attention mask to produce pixel-wise probability maps over a set of predefined spatial relations. And during training, we sample the locations UV according to gamma implant inside an auxiliary classification network, here depicted as RelNet, at the sampled locations these high-level features of the objects and classify such hallucinated scenes to get the learning signal for this spatial RelNet. And at test time, we don't use this classifier anymore. This way we can reason over what relations would most likely be formed if we place an object at a given location. And coming back to our pick and place task, so once we have grasped an object and we want to do a placing and have such an instruction, we can now first ground what is the bottom object with our first grounding network, and then we can generate different spatial heat maps for a set of spatial relations, which we can then use to generate the sampling, the object placement pose.
Robert, fetch the red thing.
And this leads to our full system where we try to do a pick and place with freeform commands. And here in this experiment,
Robert, place it behind the colored dish.
it's a bit loud, sorry.
Understood.
We have here a table from which the object should pick objects, and here it should place them.
Robert,
Here
fetch
now
the
you
yellow
see the
stuff.
user is doing an ambiguous
I'm not
instruction,
sure.
fetch the
Do you
yellow
mean
stuff,
little banana?
and now it,
Robert,
thanks to
yes.
this captioning module,
Understood.
we can query back on this ambiguity instruction. Two more implementation details here. You don't see it, but we place a
place it
second
on top
camera
of the
over
bottom
here.
object.
Maybe I will do it a bit less loud.
Understood. Placement.
We have two cameras, two RGBD cameras. We perform online registration
Robert,
to
fetch
have
the
a better
lever next
point
to the
cloud
danger.
to grasp these objects, and
I'm
we
not
use
sure. Do you mean the
a
yellow?
GPD method for generating
Robert,
the
yes.
Understood.
grasp poses.
Fetching the yellow fruit.
So these are our results for this experiment. We observed that our approach achieves a 78% accuracy in target object selection and around 85% on selecting the reference object where we want to do the placing to. This latter higher accuracy is because the users preferred to instruct ambiguous instructions for the picking task and not so much for the placing task, and also there were less objects. So, and we also report grasping performance of about 74% with GPD for a total of 63% pick and place performance. And we also did an additional experiment for a tidy up task that consisted of iteratively picking 4 colored objects from the cluttered table and placing the same colored objects on the left container and the remaining objects on the right container.
Robert,
And
place
it needed
inside the
around
left box.
14.4 actions on average to solve this task. And I'm running out of time. So
Robert,
most
place
importantly
it
also
right
are the failure modes. So
Understood. Placing.
we observe failure modes for cases of large object displacements because of missing 3D
Robert,
priors
fetch the mark near the
of
danger.
the objects to be placed. So you saw that
What else do you want?
the big box was over the small box. So we would need to add this 3D information to optimize for better object placement poses. And we also
Robert,
noted that
fetch the mark near the teddy
we
bear.
also had sometimes no feasible grasps found by GPD due to either occluded object parts or noisy measurements, especially like this mark here was a nightmare to
Robert,
grasp,
fetch the mark near the teddy bear.
like the rim.
Understood.
So it was
Fetching.
so grasping is not solved, I would say. And for conclusion, so we presented a robotic system that allows to sequentially compose pick and place language instructions and tries to disambiguate when there are unclear instructions. Our main limitation of our approach is that this is tailored to pick and place tasks. So if you would like to open the drawer, a drawer or a sliding door with language commands, it's not trivial to extend such an approach to more general manipulation tasks. And most importantly, in this work, we focused on grounding object semantics and spatial relations, but we ignored grounding the actions themselves, which is very, very important for us as a roboticist. And therefore, I would like to mention that since then we have worked more on this topic, and we are very excited now to open source a new simulated benchmark to learn long horizon language condition tasks called Calvin. And this is a very cool simulated benchmark where we recorded over 24 hours of teleoperated play data in the simulation environments for different rooms. And we provide a flexible sensor specification, so you can train multimodal agents. So with RGBD of static camera, of a gripper camera. We also provide simulated visual tactile information, similar to the ones presented yesterday. Yeah, so if you're interested, talk to me and check it out. Thanks.
We have time for questions. Oh yeah, there's one in the back.
Great presentation. Thanks for the explanation and cool work. Just curious what kind of language model you're using. The types of spatial referring expressions that you're talking about here seem to be limited to the first-person perspective, and it seems like it might be difficult to extend that to other types of spatial referring expressions. So just curious where you might be taking that.
Yeah, so this is correct. I forgot to mention one more limitation here, or assumption, is that the spatial relations are from the robot's perspective, basically. So if you would, this is actually a very interesting problem. If you want to add spatial relations from user perspective, then you need some additional logic. So if you say to my left or to your left, that you can mirror this spatial relations. We have not considered this in this work, but I know there are some previous works that consider these things. Yeah.
Just a quick follow-up on that. Yeah, and also that certain types of objects seem to have different types of orientations that are kind of attached to a coordinate frame. So you could say something is across from something else, and then you would be automatically assuming that that object has some sort of heading, which is why I was curious about.
Some sort of what, sorry?
So like if you say in front of a chair, then it always, or almost always refers to, in English, the thing that's in front of where you'd be sitting in the chair, not relative to the speaker. So then it becomes conditioned on your language model, not just on some logic that you would be applying. So that's why I was curious about what kind of language model you're using.
So are you referring to the picking or to the placing?
Well, actually, in this case, it would be, like, I just asked the question, what is the language model you're using? You had an encoder on language in the first few slides.
Yeah, so the language model is learned with this MATNET architecture. So it's
okay. Yeah.
LSTM-based model, which encodes the instruction and generates some vector, basically. So it's not like a pre-trained transformer or anything.
Got it. Okay, cool. Thanks.
Any more? Okay, I'd like to thank Iser again. And now we should have, I think I saw him, we should unmute, and Davide Lanza. Yes, is there. Okay, this is a paper titled Multisensory Integration in a Quantum-like Robot Perception Model. And, oh yeah, we have to commute. Is it? Cut, okay. Yes. Here you are. You are on stage, Davide. Good morning.
Yeah.
Go ahead.
I'm trying. Okay. I should present right now. I don't know if you see the presentation. Yeah.
Yes, perfect.
Okay. It's such a pleasure to be here at ISER, finally, even though I was not able to be in person, and that's quite sad, but I'm really happy anyway, and I hope you're having a good time. And today I will present my work that I realized with Paolo Solinas and Fulvio Mastrogiovanni at the University of Genoa, that is called Multisensory Integration in a Quantum-like Robot Perception Mode. Basically, we started from the assumption that most of quantum computing applied to robotics relies mostly on using quantum computing as a speed-up tool, or it's inserted in a framework that is still a classical one. So with the quantum robot project that this paper is part of, we tried a different approach. So that instead of starting from the advantages of quantum computers that are really known for, like speed up, we started from the inherent quantum properties, as is already been done in cognitive sciences with quantum perception and cognition models. This we argue that could be extremely useful in robotics if proven good, because it could be good even as a purely simulated model, while when we use quantum computing as a speed-up tool, we need the quantum backend. That is quite a problem to have. And then it could provide a way to translate this theoretical model from cognitive sciences to practical robotic application, or at least to have a synthetic application or synthetic alternative in order to test them further. These merits comes to the exploitation of quantum system properties rather using it as is normally being used. So we started with a preliminary model that is inspired by Manusaki's binocular rivalry model. That is a model that is made in, this is a cognitive science model that describes binocular rivalry as a superposition of two states. As we can see here from the Esker famous image, our perception of the white angel and the black devil oscillates while we are looking at it, as well as the blue and red writing, and as well as the image that seems to bend inside and outside of the screen. So what Manusakis did was associating these two states to two basic states of a quantum system made only by a single a binary basis state. And then he associated some coefficients to the certainty of uncertainty of seeing one or either one of the other, and then he associated the measurement and the collapse then of the quantum state to one of the basic states as our perception of one image, namely the black devil or the white angel. Starting from this, we started to define a first model that was monodimensional model to assess the feasibility of a quantum-like perception model such as that in order to address robot use case with limited sensing capabilities. Then we will interpret quantum measurement as a query, as we said. So then given a certain belief, we can use the quantum system as a sensory integration unit with inherent decision-making capabilities. So the low-level scenario that we choose was to have a really low-level elementary motion detection sensor that we're able to detect even either an object is in front or in the back of this fixed robot. And the single qubit in this case allowed us to store, integrate, and represent such sensorial data that in this case is a binary monodimensional data. And with monodimensional, we mean a scalar coming from a single sensor. And this single qubit model, we're encoding it inside the quantum state of the state of the quantum system, and then operating a decision on the data by measuring the system. How we were able to achieve this by using sampling a number of events inside of the temporal window. In this case, we have a temporal window of 4 events. The model acquires binary data with a specific sample rate inside this window and encodes it by rotating the state vector by the rotation operator around the y-axis that we see in the formula. And finally, the measurement gives us a binary outcome following quantum measurement probability. That is the probability of having the state associated with the front or in the back. It depends on the theta angle on the log sphere representation. That if we interpret the measurement as a decision-making process, We then realized that measuring it with the collapse on one or on either the front or the back state, we have a decision based on this data that we stored previously in the previous temporal window. So the goal of this paper was to try to generalize such an approach in order to consider multidimensional data, and especially not only binary data, but scalar data. And we tried to generalize it, and we managed for multidimensional continuous input, even though we managed to do it with normalizable inputs, so bounded inputs. And moreover, we can with this kind of approach, extending it to a multidimensional system, we can exploit more quantum properties, for example, state superposition and change of basis in order to address superpose any state made of a linear combination of its basis states in the Hilbert space. So by knowing this, we can virtually deal with any possible state. And we will see there is an analogy between the state in the Hilbert space and then the configuration of the world outside, recorded by the sensors. So in this case, at each reading update, the model will receive an n-dimensional vector of normalized scalars. And in here, for simplicity, we tried, and for visualization mostly, we considered a three-dimensional sensor that could be considered an RGB light sensor, providing three scalar values between 0 and 255. Then are normalized by an interface inside an interval between 0 and 1. So our vector will be made of three scalars in between 0 and 1. Then every qubit qi encodes the corresponding scalar input xi from the input vector. And we encode, as we saw before, data with a unitary operator that applies a rotation around the y-axis. And by doing this, we generalize it in order having a multi-qubit system that is then summed up by a single state vector that retains all the information, in this case by all the three dimensions. So the information is encoded, and there are many indirect methods available in order to exploit such information. We still use measurement as a way to extract information based on the measurement as a decision-making interpretation, but we also have many other methods in order to address this information stored in the state vector that we will further investigate. So in this case, for example, we have a superposition of states, and the first diagram, in the first diagram, we can see the coefficients related to each basis states in our three-dimensional model. And so the probability of the state collapsing after the measurement to a certain basis states is given by the current superposition. As we see, the measurement probability is directly linked to the coefficients in the state vector. And due to our encoding via the rotation operator along the y-axis, such probability is then related to the input vector that is being retained along the temporal window. So, considering our RGB example, we can associate the basis state with the 8 bound values of the RGB states. We can say, for example, we have a certain sensor configuration that is associated with a certain color, and then we can associate all the bases to every state of the base a certain color. And then we see how the probability of a certain input is then linked to any basis, to the measurement of a certain basis vector. Of course, more bluish one color would give more probable outcomes with the blue state and so on. But this is not the best achievement of such approach. But as we saw before, since we have a superposition state, and the superposition state is itself a state in the Hilbert state, that state has a physical meaning by its own. So we can define a query operator that addressing a specific target that we call here x bar. And by applying an inverse rotation, we can operate a basis change in order to directly map the basic state 0, 0, 0 to our target state. In this case, we use this kind of violet, and we see how then we can query how much an input could be a certain target, and we have some measurement, and then we have the measurement probability associated with that. As we see here, though, like by operating the query, we lose the correspondence between all the other basis states. So we lose their analogical meaning that they retain in the original configuration. Nevertheless, we notice that the number of zeros of the measured states is still like corresponding to the similarity. In fact, here we can see like a graph on which on the y we have the probability of measuring a certain state, that is the 0, 0, 0 state, the state with 2 zeros, the state with 1, 0, and then the opposite state 1, 1, 1. And then on the x, we have the Euclidean distance between the two RGB vectors, the input one and the target one. And the more they are far, the more one we will have, like when we measure, the more likely we will have a one or a more one state, a basis state made more by one when we will measure the system. So this gives a nonlinear yet definite correspondence between stored information and measurement. And this is important because it allows us to use the n-qubit system as a multidimensional data integrator, and which inherently provides a coherent representation for the n-scalar input, a similarity metric relying on the geometric properties of the Hilbert space, and the quantum decision process that is inherent to the measurement process, and is based upon this metric. That is to say, it's kind of like a garden for space, but is instead made of a Hilbert space, and which retains directly similarity metrics, and this similarity matrix is directly associated to that decision process that is the measurement one. So with the query operator, we can extend such behavior to every state, and this allows a compact and elegant representation that allows to address any state and any comparison and any query between any two vectors in this space. Indeed, even if the probability distribution in the figures refer to the basis state that is in its original configuration, that is the 0, 0, 0 state, this can be easily generalized, so we can imagine the probability density shifting along the RGB cube. But the limit of this encoding still is that targeting states with queries that span not all the RGB cube, but there are, let's say, in the middle of RGB cube, will likely give readings which have at least 1 0. So we will not have like a narrow discrimination in between them. Indeed, like further work is right now investigating if either it's possible to narrow these probability curves for targeting states that can then lead to a more steep probability curve. Or then we can show that this is not like an obstacle in practical application by applying it in use cases that will show that this is not a problem. Moreover, we're working on a modular architectural framework on the quantum robot project that is made of like n-dimensional quantum system as the one we defined here, that are like made in a framework, in a cascade framework, like in a network-like fashion, when we have sensor interfaces that normalize the input from the scalar sensor input, and then they are linked to the first layer of units that we call perception unit. And then these units were made by measuring this unit, a burst will come out and then will be fed to another unit, and so on, until we have then actuator interfaces that will gather results from some of these units, and then will perform a certain action. So this is where the project is heading right now, and I thank you very much for your attention. I hope I was not too like over time, and I welcome any questions.
Thanks very much, Davide. Cosimo, you have a question.
Thanks, Davide. Super interesting talk. I think, I mean, the idea of using quantum machinery to implement it in a classic computer, I think it's quite appealing also for robotics. But I wonder, I mean, in the end, if you could comment, which are the differences if you do something like that with respect to the nowadays more classic probabilistic robotics?
I would argue that most of the advantages right now are from a model perspective. Like we have a coherent way to represent data and to integrate it and then to operate a decision on it that is all retained by the single quantum system that in this case is simulated, rather than having a modular architecture with different kind of elements. That is to say, like, since this is pretty like monolithic, we can then use it to then define it like units that retain information and deal with information like in this way, but then they are like self-living units in this way, and in this case. So in my opinion, the advantage is more like we have a way to easily deal with integrating information and decision making that is inherently provided by the quantum system. So we don't need then to further specify any ad hoc modular modules. And then this allows us to use it as a bricks in order to build this larger framework.
So in the interest of time, I'd like to thank David again and just give him another hand. Thanks, Davide. And we move on to the next one, which is by Fabian Paus. The paper title is Probabilistic Representation of Objects and Their Support Relations. And Fabian is here. We have to switch. Okay, here we go.
Yeah, thanks for the introduction.
Oh, yeah,
Yeah, thanks for the introduction. As I said, my name is Fabian Paus. I'm from the Karlsruhe Institute of Technology. And what I'm talking about is understanding scenes with multiple stacked objects. So if you think about humans are actually able to very early understand what it means that an object is well supported. And neuroscience tells us that it's even like starts at the age of 3 to 12 months. And you can see a small child here being able to stack objects on top of each other. And what results from neuroscience tells us that they start with first understanding like what it means to be in contact and not in contact, and then they get to reason about supported surface areas and so on. So once we get older, we humans are able to understand even more complex systems, and what neuroscience here tells us is one key ingredient into human intelligence is what's called combinatorial generalization. So we can represent complex systems as objects and relations and then abstract from that. So you might not have seen this exact stack of cutlery or this exact configuration of a Jenga tower, but since you are able to understand what it means that an object is supported, you can understand which of these objects you could pick up safely and which not. And the questions that I want to look into my research is like, how can we equip especially a humanoid robot with these cognitive abilities that are apparent in us humans? So the main idea is if we can give a robot an understanding of what it means that an object is supported by another and understand these support relations, this should enable a robot to predict what happens if it interacts with a scene, but also to manipulate the scene effectively. And the robot starts with like a perception of the scene in the form of a point cloud. And what we want to do is understand what are the objects in that scene, understand their poses, their geometry, understand the relations between them, and then we can do prediction and manipulation. And derived from that are the research questions that were addressed in our paper this time. Is like, how can we represent the objects and relations while capturing the uncertainty into the object shapes, poses, and relation existence? Because, of course, we can't really know the exact dimensions and poses of every object in the scene. So we need probabilistic geometric shape models for the objects that we have there, and we also need a probabilistic representation for the support relations, because we can't be sure that support exists, but we can only assign a probability. Yeah, so as I said, our approach starts with the point cloud that we capture from the scene, and we segment it using state-of-the-art methods to get object candidates. So this is not part of this paper, but it starts basically here with the RANSAC. So we modified the RANSAC a bit to actually not give us a single estimate for the geometries of the objects in the scene, but a distribution over the geometries. And from this distribution, we can sample concrete scenes
And in these concrete scenes, we can then analyze whether support exists between objects, do statistics, and then extract a probabilistic representation of these support relations in form of graph. So to go into details, so RANSAC is usually used to fit a model giving data points, and it just selects random data points and then fits the model, counts the inliers, and picks the model that has the most inliers in the end. And in this work, we extended it a little bit. Instead of only taking the best fit in the end, we also consider all the other fits that were generated during the RANSAC in order to estimate not only like the mean, but also the covariance of the scene distribution. And how does this distribution look like? So for each of the point cloud segments that we got, we have to get a probability distribution over the possible primitive types and their geometric parameters. So in this work, we only considered boxes, cylinders, and spheres, but every geometric model that is parameterizable can be used in this fashion. And conditioned on a discrete probability distribution over the types, we also have a multivariate Gaussian distribution over the geometric parameters. So for example, a sphere has a position and a radius, and cylinders and boxes have more parameters. So then the complete probability distribution is the combination of those two. So given this scene, we want to understand the scene distribution, we want to understand which object is supported by another. And first, we're going to ignore the distribution part and only look at concrete scenes. So one approach in state-of-the-art to understand support relations is to look at the forces that are exerted in the scene due to gravity. And we also rely on this as a basis. So this works so that we first detect contacts between the objects. These are the red squares that you can see, and then separating planes are introduced, and then we look at which object exerts a force due to gravity onto another object. And if this is the case, then we assume that this is supported by the other object. This, of course, only captures like bottom-up support, so if a lower object supports an object farther up. And in the previous work, we also considered cases if we consider this object arrangement. When you remove an object on top, like the object B, then it might be the case that the object A will also fall, of course, depending on mass distribution and so on. And this cannot be captured by this naive analysis method that I shown before. And so in order to catch also these cases, we introduced a support polygon analysis where we look at this object A projected to the ground, find the support polygon. So the support polygon is like the intersection between the objects that are supporting object A, and then we look at how much of the object is actually supported, so some kind of support area ratio. Of course, you could do something more intelligent if you knew the mass distribution of the objects and so on, but this is like where this support area inspiration from neuroscience comes from. Something similar is done by humans if they analyze scenes. Of course, this only works in like if we know the exact scene geometry. So before I've shown you that we have now a distribution of scenes that we got from the point cloud and the RANSAC, and now we want to know the probability that a support relation exists between two objects. And for this, we just made a Monte Carlo simulation. So we sample from the scene, and then we have concrete scenes. We can use the support relation analysis method that I've shown you before. And then it's just summing up the concrete support relations that existed in these samples and averaging them. Yeah, so how did we evaluate this? So we have a small data set that was part of the paper and then extended an existing data set. It's mostly scenes with like objects on a table and that are supporting each other. And the metrics that we looked at are precision and recall, which are like binary metrics. So, and the Bria score, which actually takes into account the predicted probabilities. Precision and recall get higher. So the best score would be 1.0, and the worst score would be 0.1. And the Bria score is more an error metric. You can see it here. It's basically just the squared error of the predicted probabilities. And so this is an ablation study where we first see the reimplementation of one of the state-of-the-art methods, the force analysis method. then our previous work with the support polygon analysis, and then also now the probabilistic representation that I've shown you. And you can see that our previous work improved precision recall and the BRIA score, but compared to the smaller step from the support polygon analysis, this probabilistic representation actually really helps to improve precision and recall, but even more significantly, the BRIA score that actually takes into account the predicted probabilities. Which means that if we predict the probability instead of binarizing it for the precision and recall, the results are even better. So the question is, what can we do with that? So here's more like a proof of concept, what we can do with it in a pick-and-place task. We want to use these support relations to predict action effects and then plain safe manipulation actions. So this small example, you can imagine if the robot picks up this yellow sugar box, then maybe the cracker box will fall. So we can use a bimanual manipulation strategy. And then if the object falls, we can detect it with the force sensors of the robot. That's the idea. So here's more the proof of concept, where you can see the task of the robot is pick the Pringles, the chip scan, and the robot has to now use the support relation that it has extracted to determine now it's a good idea to support the light blue box during this pick task with the other hand. This, of course, now for us, it's easy since we work with the humanoid robot, so we have another hand to support the object. But the problem is if we now in this configuration, the question remains what to do once we are in there. So now the robot can't use his left hand anymore, right? So maybe we need to do this in another way. So this is not completely solved. This is also where Oya is doing work. Where do we place objects in order to create certain relations between objects? It's also something we are still working on. So now the robot places it on top. But this is as I said, more proof of concept. We are working on how to actually do this in a rigorous manner to know where to place objects. So I've shown you a probabilistic representation of object geometries and support relations that captures uncertainty and improves the support detection results significantly. Also some work that we do in the experiments, working what can the robot do with these support relations, and some future work, more in the future. Some people in our lab are working on natural language, similar to Oya, for commands to alter the scene state in a particular way, like how do we stack objects so that they are still safely supported by the objects below them. Explainability, so we can use these support relations and prediction models to understand and to give the robot the ability to explain why it took an action. So I didn't put my hand there because I didn't think it would fall. So the robot can explain why it succeeded or why it failed afterwards. So these are things that we are working on in our lab. So the code, the data, and some reproduction guide is all available. And of course, this work has been supported by some European and German agencies. So thank you for your attention.
Time for, oh yes, we have one question in the middle.
Hi, I'm curious why you normalized the parameters of the objects and didn't just sample them, because it seemed like you were only sampling from those distributions, and you built them from particle distribution.
I didn't get the first part.
I was just curious why you normalized the geometric parameters that you get from RANSAC and not just sample them directly for the later use when you sample to get the support relations.
Okay, so sorry, I didn't get what you mean by normalize. So I think I understand.
You compute you take the mean and the covariance. Yeah. Why you didn't just sample the output from RANSAC directly if you have a particle representation?
So I skipped a little bit too over that. So they are actually weighted by their error. So if you just pick random points, the geometry is usually worse and gets a low inlier ratio and a big error. So they are weighted less than better models. So of course this could also be directly done for the support relations. Yeah, you're right. Yeah, so it's more like the pipeline approach if we want to use these object models for something else, but you're right, we could directly use them weighted for the support relation estimation. Yeah, that's a good idea. Yeah, thank you. Thank you.
Any more? Oh, Cosimo.
Yeah. Okay. Yeah, on a very related point, you use Gaussian distribution there. I wonder why. So, because I guess that most of uncertainties are going to be asymmetrical, so not well captured by Gaussian distribution, and in the end you end up sampling the distribution. So, which is the advantage?
So this was more like to have a simple representation. I didn't put now much work into what to use, so I would be very interested in what better distribution could be used, or something similar to suggested there to actually to have the true samples used for that. Yeah, so this could be really interesting in the future, I think. So it was basically the simplest thing to do, but I agree it's not could be the wrong tool here. Yeah.
Okay, thanks very much again, Fabian. And our next paper is titled MSL Raptor, a 6 degree of freedom relative pose tracker for onboard robotic perception, and it will be presented by Benjamin Ramtola. Please. Yeah, use the mic, yeah.
Yeah. All good?
Go.
So hi everyone, I'm Benjamin and I'll be presenting MSL Raptor, which is some joint work I developed in collaboration with Adam Cacavalli and for which we were supervised by Giovanni Beltrame and Max Schwager. And as you can see in the title, MSL Raptor is a 6 degrees of freedom relative pose tracker that you can use on board robots. And so why are we interested in relative pose tracking in the first place? So it's a very important perception module that serves for many tasks, such as the few ones I chose to illustrate here. Relative pose estimation is the estimation of the 3D position and orientation of objects with respect to the robot's ego frame. And so in mapping, it can be useful to keep track of where objects were in the map. In object manipulation, as we've seen with other works, it can be helpful to know where to go and grasp the object. And in autonomous drone racing, it can be useful to avoid colliding and try to plan and pass another drone. But for a relative pose estimation system to be usable in all those situations, there are a few properties we'd like it to have. One of them is that it should be fast enough to be used on board and provide frequent enough estimates. It would have to rely on inexpensive, commonly available, and low energy sensors. If you think I wanted to do that on a small quadcopter that doesn't have a big battery, it would ideally be easy to use on a new scenario with new objects to track that we've never used it for before. And it would provide uncertainty estimates that would be able to be given to downstream tasks such as controller planning that could make use of those. And so it's with all these requirements that we designed MSL Raptor. If you want to use MSL Raptor on a new object you've never used it for before, you just need two things. The first thing is to approximate the shape of the object you want to track, and that can be as simple as the 8 corners of a 3D bounding box around that object. So for this drone, for example, we just measured its 3 dimensions, and we had the bounding box and could use the 8 corners to now try and track it. And the second thing is an object detector that can find where the object is in a single image and provide a bounding box around it. And so MSL Raptor takes in sequences of monocular images, will feed them to a deep learning-based front end that will extract bounding box around the object of interest in those images. These will then be used, so these are 2D bounding box and images, and they will be used as measurements in the UKF, unscented common filter backend, that will be the one providing actual 3D pose estimates alongside uncertainties. And as a side effect, we also get bounding box uncertainties from the UKF that we can reuse to improve the front end and make it more robust. And the core idea of why this can work is because there is a relationship between how the 3D pose of an object changes and the 2D projected bounding box changes. So here are a few illustrations. If you see a bounding box that's to the right of what you'd expect, that could indicate the translation in the 3D world of the drone. If you see a bounding box that is a bit smaller, that could indicate that the drone is further away than what you'd expect. If you see an aspect ratio change of the bounding box while keeping the same width, that could be an indication of orientation change. And as you can imagine, there's a lot of ambiguities here, and we can't really relate one pose to one bounding box. But thanks to the filtering approach in the UKF and the fact that we have sequence of measurements, MSL Raptor can still work decently well. And one of the things we use to actually reduce those ambiguities is the angled bounding boxes rather than the often seen axis aligned ones. And it's very visual. You can see that having this angle reduces a lot the ambiguities. The two first poses would have the same measurement, but the two ones in the bottom with the angle don't. So it's not perfect. We still have many ambiguities, but it is very helpful for MSL Raptor already. So I mentioned that the front end of MSL Raptor takes in sequences of monocular images, and it provides bounding boxes, and it does that with two main modules. The first one is the detector. It's one of the things I mentioned. We assumed we had to get it working on a new object, and the detector takes in one image and provides a bounding box around it. We also use the 2D tracker, and the tracker doesn't have to be trained specifically for the object you want to use, but it is initialized with the bounding box around the object to track. And in our experience, the tracker is actually more accurate and faster than the detector, so we want to use it as much as possible. However, it can get confused, in which case we have to reinitialize it, and that's why we use a combination of detector and tracker in MSL Raptor. And you can see this in action in this video. So we're showing the front-end output with a box around the drone that we're trying to track. And when it's green, it's that we're using the tracker output, and you'll see it blink in red whenever we reinitialize the tracker using the detector. So there are 3 times we will use the detector. There's when we initialize the tracker in the very first place. There is just periodic redetection to make sure the drone or the object we're tracking is still in frame or we haven't lost track of it. And there is one that is informed by the backend measurement uncertainties we get, which allow us to figure out if maybe the tracker got confused. And you can see it in action here. So yeah. Basically, it does get confused sometimes, but it always ends up recovering. We switch back to detection sometimes very quickly after getting confused, and this makes for a pretty robust system. So it's not perfect, but in an application, it would be robust and be able to recover when it does get lost. So that's the front end, and it provides 2D bounding box measurements. And as I mentioned, we use a UKF in the backend to convert those to relative pose estimates in the 3D world, so 3D position and orientation. And so we do that by keeping an unscented Kalman filter for each object we're trying to track. And that UKF is class-specific because we get class information from the detector. So we're able to use class-specific parameters when we're trying to track their backend. And so for the state of the UKF, we have the relative pose in terms of position and orientation, and we also try to keep track of the velocities, which is helpful for the dynamics. So by default, we use a constant velocity model, but you're able to adjust the dynamics to any object you want to track. So if you have a prior about, for example, keeping cars flat on the road, you could have that in your dynamics of the backend as well. And for the measurement prediction, we use the second thing I mentioned we assume we have, which is an approximate shape of the object in terms of a few set of points. And then we can project those using camera intrinsics to the image plane and figure out what the smallest bounding box fitting those points is and use that as our measurement prediction in the UKF, which allows us to do all the UKF update rules, which provide the final poses and measurement uncertainties. So that's how MSL Raptor works. The first experiment we did was just trying to compare it to what the best relative pose solutions were at the time of writing this paper. And we used the Knox Real 275 dataset for that, which is basically sequences where you have a camera moving around the static scene with different objects in them. These are the 6 classes of object we can observe. For the 3 leftmost one, we can approximate them with a 3D bounding box. For the 3 rightmost, we did minor adjustments to the shape we used for approximation, but they're still very coarse and approximate. Here you can see how we compare to other baselines. So our translation error was 8.2 centimeters, the median translation error. It's not the best. Six-pack was actually significantly better in those situations, but it's also not the worst. So ICP does a lot worse. But the interesting bit here is that all these methods use RGBD data, so they have a depth channel that they can use to estimate how far the object is, whereas MSL Raptor can only get depth information from the size of the bounding box and the prior shape we give it. So it's actually a lot more of a challenging task for us, and we were very happy to see that MSL Raptor still gets in the same range of errors as all these baselines that use RGBD data. So now the experiment we were really interested about is an actual onboard robotics experiment. So we had this set up with 2 drones flying in a room, and one of the drones was trying to estimate the relative pose of the other drone with respect to it. So we approximated the shape of the drone with a 3D box, as I mentioned earlier. And then we tried to do onboard relative pose estimation using the NVIDIA Jetson TX2 and the monocular camera we had on the drone. And we compared that to the fastest monocular relative pose estimation solution we could find at the time, which is called single-shot pose. And how single-shot pose works is by training a neural net from relative pose data that tries to predict the 3D bounding box directly from the image of the object. So it's trained specifically for each object, and then tries to predict the corners of the 3D box, and then it uses perspective and point to recover the pose from that. And we also ran it on board the TX2 online, and you can see the results here. So these curves illustrate the percentage of estimates within a specific translation or angular error. And you can see that MSL Raptor does a lot better than SSP in this experiment. So not even 60% of the estimates of SSP are within 3 meters of translation errors. And this is due to the actual practical aspects that happen in this experiment. You can see an illustration of the predicted bounding box from the neural net in red here from SSP. And because in our situation we don't have a super high resolution camera because we're on a drone, and the drone gets pretty far and it's moving pretty fast, the images are sometimes blurry. I guess even for us, it's hard to tell that there is a drone here because that single frame was a bit hard to estimate. Well, it was very blurry. So that leads to very distorted 3D bounding boxes from the neural net, and the PNP recovery of the pose is then gets very large errors. Whereas MSL Raptor, thanks to the tracking in the backend, is able to still get decent estimates even in those challenging considerations, situations where the measurement is pretty noisy. The final metrics are here. So we get 82 centimeters of median translation error. Most of that is actually in the depth, like how far away the drone is that we get noise. And that's only a third of what SSP gets. And we're running on board online on the drone at almost 9 hertz, whereas SSP, which was the fastest alternative we could find, was only at 3 hertz. And you can see a visualization of our predictions on this video. So it's not perfect. Sometimes it takes a bit of time to find the right depth, how far the object should be. But overall, it is pretty robust, and it is a decent estimate. We think I think we can already be used for many robotics tasks, especially considering this is running online at 9 hertz on a small drone, using a monocular camera only. So these are the results you can find in the ISCR paper in the proceedings. We did make a few improvements since then. One of them was trying to speed up MSL Raptor. So we did a few implementation changes and used a different object detector with a niche GPU accelerator. And we got MSL Raptor running on board the drone at more than 50 hertz. And this was used to be included in Team CoStar's pipeline for the DARPA Subterranean Challenge. So I think it was mentioned already, but just in case. So it's a competition where teams have to send robots to explore unknown environments. And there are objects in the environments, and we score points by finding where the objects are and reporting their position accurately. So one of the things you have to do to score points is to estimate where the objects are relative to the robots that are near them. And so Team CoStar's method for doing that, the default method uses depth data, which is great when it works. It's pretty accurate. It's more accurate than MSL Raptor when you do have that depth data. But we were worried about situations where we would not be able to rely on depth because maybe we had sensor failures or communication failures, or objects were far and the depth data was noisy, or we had a small drone that wouldn't have a depth sensor. So we included MSL Raptor in the CoStar pipeline as a fallback method for when depth wasn't available. And it was a really cool application for us to see because it actually made use of all the aspects we tried to design MSL Raptor to have, such as being able to adapt to new objects pretty easily, such as not needing a lot of data, such as being able to run unlimited hardware. Okay, that was it. Thank you very much. Please go ahead with your question.
Time for questions. Yeah, we have 2 in the front and 1 in the back. Maybe 3 in the front, yeah. Like a mic. Yes. Thank you.
Thank you very much. It was really interesting. I would like to ask, what happens if we change the drone? Do we need to train the model again, or what is the input to the algorithm?
Yeah, so if you want to try on something completely new, you need 2 things. One of them is approximate the shape. So if it's your drone, the 3D box works pretty well, which means you can just measure the size of your drone and get the points from that, the 8 corners of a bounding box. And for the object detector, it depends on what object you're using. So because it's just an object detector, there are plenty of pre-trained models out there. So for some experiments, if you're doing like a mug or I don't know, whatever exists in the COCO dataset or ImageNet, you might be able to, maybe not measure, but yeah, you might be able to find a pre-trained model. For drones specifically, there weren't many data sets we could find, so we trained specifically on our drone, and our detector probably wouldn't adjust to new drones. But if there is a data set with drone images out there that is labeled, you could just use that one, and you wouldn't have to probably retrain for your specific drone.
And is it open source available, or
There is a version of it, but not the final and best one. So if you actually want to use it, reach out to me and we can figure out how we should do it.
Thank you very much.
Sure.
Thank you, Benjamin, for the nice presentation. I think you answered most of the questions that I wanted to ask. So the deep learning neural network that you use, so that's a contribution of this paper. Right? You're not using any existing method.
Those are existing. So for the detector, we end up using GoV3, and for the tracker, SciMask.
Okay.
But yeah, these are like modules you can switch around. So for the sub-T challenge, they had their own object detector, so we ended up using what they had. So I didn't really highlight which solutions we were using, yeah.
Okay, got it. Thank you.
Sure.
Very quick follow-up to that. YOLO only does bounding boxes by doing, extents on the bounding box. How do you do the tilt on the bounding box?
So I don't know if you know SciMask. It's the tracker we use, and it's really good in practice if you want to use it on your thing. So once it's initialized, it will already provide a segmentation around the object that it has to track, and so we use that. So whenever we detected, we already initialized the tracker as well, and that gave us the segmentation which leads to the angled bounding box. Sure.
Yeah, I had a question also. Very nice work. I had a question about how you're feeding the measurements from that network into the UKF and how you choose the measurement covariances, especially in the case where the tracker kind of loses the drone for a second. Do you consider those covariances to be static, or do you update them?
In these experiments, they were static. So the measurements are just the parameters of the bounding boxes, so width, height, position, and angle. And yeah, we manually tuned them for this experiment. It worked pretty well. We would reinitialize the whole UKF when we are too confused. Yeah, we didn't have any issues with that, but probably in more serious applications, we would consider changing them online, yeah.
Okay, thanks very much again. So the next presentation is by Lucas Meyer, and it's robust vision-based pose correction for robotic manipulator using active markers.
So, hi. Hi, I'm Lucas, and I'm going to present today our work on robust vision-based pose correction for robotic manipulator using active markers. First of all, about our setup, our scenario, we have our lightweight rover unit, which is a planetary exploration prototype, and it is used in Moon or Mars analog settings for manipulation tasks. Theoretically, there should be slides coming up. Okay, yeah. And it has a lightweight design, which is very desirable in many cases. However, it also has some drawbacks. For example, it introduces elasticities in our system, and those lead to inaccuracies in our kinematic chain. For example, like from the camera to the tip of the robot. So the arm never really appears in the camera image where you actually want it to be. So the task is we have to correct somehow this kinematic error using vision and considering the outdoors applications. For example, working here on top of a volcano. In this case, it was in Sicily, Italy. Our constraints are that, like I said before, we have to consider outdoor operations, mostly strong illumination and reflections. We have monocular measurements. And we have very limited computational resources as everything is running on board of the system and there are many processes in parallel. So we have to find a very minimalistic approach that we can use in our next mission. Next year we are going to the volcano again, and there this component should be used. So to solve this problem, we said, okay, we want to combine the kinematics and the vision. And from the kinematics, we can select a region of interest, run our detection, where is actually the tip of the arm, and then fuse it all together. And one of the major assumptions we have is that our kinematic error is locally constant. So if we once correct the kinematic error in the arm, we can mostly rely on our cheap high-frequency kinematics and only need to update it when the pose of the arm really changes again. So we can really have low-frequency vision updates and focus on the kinematics. For the vision, you can see here some example shots from our robot camera. We can use the active markers that are at the tip of our robot. And due to the outdoor conditions and generally highly varying illumination conditions, active markers in our case are not necessarily the brightest elements. However, they have the highest convergence of the gradient field, which you can see here in the bottom row. So meaning in almost any conditions, you really have a convergence in the gradient field, and if you can measure this convergence, you can find those markers. For this, we took a solution from medical image computer vision, which is called the Iris filter that searches for such a convergence in the gradient field. And it works that for each pixel, we sample along rays, and we measure the angle between each ray and the corresponding pixels, the gradient of the corresponding pixels we traverse along, and together with the magnitude of each gradient. How does this work in practice? We can see here a scene of our robot, and we select a region of interest where you can clearly see, okay, there are so many saturated pixels. This is actually quite an easy image, but it can get worse. So we can't really find the maxima. However, running the convergence filter, we can clearly see now the active markers. And then we can use RANSAC and some other outlier criteria to actually fit there an ellipse. And from the ellipse, you can theoretically extract a 6D pose. However, this is very noisy, but which is robust is actually a center of the ellipse, which is the center also of our TCP. So if we can only use those 2D measurements and not the 6D pose, we get very nice measurements that have low noise. So for integrating this measurement in our kinematics, we have to first of all look on how to actually model the error. And for this, I have to just go back to some terms. We have pose, which is an element of SE3, like the special Euclidean group, which I guess all of you know as a homogeneous transformation. So it's just a homogeneous transformation. However, if we have an error, like a perturbation, this error is not a pose, but instead it is is represented in its tangent space. This means basically a local linear representation around a pose. And in this tangent space, we can formulate this perturbation as Gaussian and insert it into our kinematic chain. So right now, for example, we consider the base error, and this base error is marked here in orange, and it lies here in between the kinematic chain. But how can we actually use this now in our measurement? We have to propagate it actually to the place where we obtain the measurements, meaning we have to somehow propagate this perturbation to the TCP, which can be done using the so-called adjoint, like working on the tangent space. And if you then take this Gaussian ellipse from the tangent space and put it back into your SE3, you suddenly get this nice banana shape at the TCP. And having this banana shape and having 2D measurements from the camera, looking directly onto this banana turns out to be a well-conditioned problem for estimating. So we can use this in an EKF. I will just go quickly over it. The system state is the pose of the TCP. And we have to keep in mind that evolves on SE3. So each update we do has to be a valid pose, meaning we don't just add there an increment. However, we add the increment via the exponential map. And the measurement model is basically the 2D pinhole protection in the camera of the center of our frame. Having all of this together, we can now see our application. So here is an outdoor experiment. It was supposed to be on the volcano, but obviously due to Corona, it got delayed. So now we have to see our nice backyard of the Institute, which is almost as beautiful. And every time you see here the yellow circle, it means that we get a valid update. And the small gray frame is the original pure feed-forward kinematics, and this RGB frame is our corrected pose. And you can also see that the ellipse is quite noisy, however, the center is quite stable, and it gives us a nice correction of the pose. For the accuracy, we had some indoor experiments having Viking as a ground truth. First of all, you can see the blue line, which is the pure forward kinematics, and also the purple line, which actually measures the extension of the arm, meaning the further the arm is extended, the more the gravity causes a deflection, and you can really see how those two errors correlate. And contrary to this, our fusion has a much better result, only failing or only getting bad in a few occasions, which are marked in gray, where we have occlusions. And coming back to this, and here for the interested, you can also see how the covariance evolves in this estimating step. So you can see that the prediction in orange from the forward kinematics is really some kind of a surface at the TCP, and then we have 2D measurements which really select the correction on the surface, or almost surface, and leaving only a high uncertainty in the depth, because of course we have the 2D measurements. However, the mean there is still correctly placed and from the forward kinematics. And the minimalistic approach I mentioned before is saying that the error is locally constant, so we can only run this vision update every few seconds, which you can see in this example, and the corrected TCP frame still stays there nicely in place. Finally, a few conclusions and lessons learned. We managed to get there a robust lightweight algorithm where we believe that it will work on top of a mountain in this moon analog setup. And what I found most interesting about this problem is that you really looked at the robot working and considering the underlying nature of the problem. So first of all, we had to find or select what is actually characteristic of this vision problem. So finding a special solution. And then also keeping in mind that robot kinematics are super rich in information and they are computationally very cheap. So rely on the vision as little as possible. And finally, the most important aspect is that even though the kinematic error, for example, happens in the base, you can't measure it at a base. You have to go and to the TCP, consider how it propagates to the TCP, because there you can measure it. And only after having this formulation, it was actually quite easy to solve the problem. Thank you very much.
Good. Open for discussion. Andrew.
Thank you for the presentation. It's very interesting work. I'm curious, when you were describing the process of fitting the ellipse to your active markers and estimating the pose of the manipulator from that ellipse, you mentioned you get the 6 degree of freedom pose, a 6 degree freedom pose estimate from that fitted ellipse. But it seems to me that there'd be an ambiguity in rotation around the axis normal to the ellipse. Did I miss something in how that's put together?
So basically, in the end, I chose to just get the 2D information of the center of the ellipse, because this was the least noisy thing. And we tried several things, and the best one was selecting the individual markers and running a PNP on it. And then you get from this model-based motivated PNP, you can get then the 6D pose.
Oh, so are you able to identify individual markers in the ellipse? Like,
exactly.
Are there distinctions between the markers, I guess?
No, they're not distinctions, but like you've seen in this error modeling, the biggest error is actually this translation. So once you can correct for this translation by fitting the ellipse in, then you can select the individual markers to get a 6D pose. But then it turned out that this is quite noisy, and just using the 2D measurements actually provides a nice estimation algorithm, so we skipped the 6D pose.
Okay, thank you.
Yeah.
Very good. Thank you so much, Lucas,
Thank you.
again. Yeah. Last but not least, Cosimo della Santina from Netherlands, sensing soft robot shape using inertial measurement units and experimental investigation. Yes.
Okay, thank you very much, Bruno, for the introduction. So this is a work that started when Josie and myself were postdocs at MIT with Daniela. So, and continued over the years. So Josie and our PhD student Francesco are the actual authors of the work. Let's say I'm just the guy in the middle that is presenting today. So, talking about soft robotics, let's be clear what we mean, at least with soft robotics. So, in our definition, soft robots are any kind of robotic system where you start introducing some kind of elasticity or softness into the mechanism. There are these two kinds. Of the second kind I'm going to talk tomorrow. Today I'm going to talk about continuum soft robots. So they are soft robots inspired by invertebrate animals. So with continuum soft part, like octopus-like systems. And perception is quite a big challenge, still a grand challenge in soft robotics, because you can imagine all the stuff that we typically use in classic robots to perceive your own body. It's no more applicable here because the state is distributed, and because for many technological issues, and also because you don't want to make the robot rigid by adding too much of rigid components to the system. So what we investigate here is the possibility of accepting to introduce at least a little bit of rigidity by considering using IMUs, and see if you can combine these well-established sensing modalities with some understanding of how these robots behaves to estimate the full shape of the robot. So, in a nutshell, what we do is that we take our soft robots, so something like that, we add a bunch of IMUs over the robot body. Of course, IMU, we all know, provide a bunch of information like angular rotation, acceleration, and we use very nice, like state-of-the-art filters, asset filters, to extract absolute rotations from IMUs. Then I mean, you can repeat this for all these IMUs along the body, and then you can combine them to know the relatively rotation among one IMU and the following one. But now you want to go from this collection of rotation, assuming that they are precise enough, to a full description of the shape. So this blue line, black blue line here. So how we do that? Yeah, with a bunch of stuff, but the main idea is that you can exploit the understanding of how the kinematic model of these systems, and this is true also for standard robots, but it becomes evident for continuum soft robots that you can really see the kinematic model as a sort of a way to generating a sort of model-based embedding or latent space. So you can really pinpoint a very small dimensional set of variables that that you can move around and obtain the full shapes that you can observe. I will go very fast on that. Really, in a nutshell, what we do. I mean, the kinematic model that we use is something that we proposed in previous work, is a variation on the 3D PCC, so piecewise constant curvature model. So the idea is that you can take your robot, you the robot in general is, soft robot is represented, the state, the configuration is a continuum function in space, in 3D, and you approximate it as a sequence of arc of a circles, and then you can take, there are different choices on how to represent these arcles of a circle, but what we do is that we measure these distances and we subtract them, but in the end the important thing is that these two variables, delta x and delta y, represents how much you are bending in each of the two directions, and really are some kind of distributed generalization of standard revolute joints. And in the end, we can go back on a good old SE3, so some rotation matrix and some translation to mapping each point of, for example, this one is mapping each point along the backbone with respect to the base of the robot, of the segment. So once you have this description, you can first take your rotation matrix and do first a projection. I mean, all these possible rotations define a manifold, and what we are doing is a projection on that manifold because the rotation that you are going to find is most probably not coherent with your model due to some small errors. But I mean, you can do a projection. But what is But what is then particularly interesting is that you can go back, so you can do a map of inverse kinematic. You go into this kind of latent space, and then you do the forward kinematics for each point along the shape of the robot, and in this way you can obtain the full description of the robot configuration. So that's enough for equations. We want to do experimental robotics here, so we built soft continuum robot that was in our mind ideal to test this stuff, and you have 3 motors. This is just one segment. I mean, you have 3 motors, and you can extend these 3 thingy, and we put one IMU on the top and one IMU on the base. And by moving 3 motors around, you can kind of make this guy bend in all directions. Yeah, and these are just some example of bending. You can also obtain a very nice extreme extension. And again, what we want to get is by only reading at IMUs, having a understanding of the full deformation state of this guy. And we also built it in a way that you can also place inside some markers for a motion capture system so that we can use it as a ground truth. Yeah, so this only to give some visual understanding of what it's happening. So this is on the left is what the robot's doing, and on the right is how our algorithm estimates its performance. I mean, its shape, and that's all quite real time. And this is instead in 2D, sorry, in 2 segments. This is actually a different robot that we built after this paper was accepted, and is a more standard like a silicon-made soft robot. But still, you can see. We have one IMU on the base, one IMU here, and one IMU here, and you can get these very reliable real-time predictions of the shape of the robot. So what we want to do is to see, is this actually useful to do some closed loop control? So we do well-known click, so closed loop inverse kinematics, and we want to check if by actually closing the loop, by the estimation that we get better performance in tracking, in moving the tip of the robot around. And these are, the tasks here that you see here are like Cartesian motions in these three directions, while the other 2 Cartesian variables are constants, and you can always see a quite nice improvement in the tracking performance. while using our IMU approach. Yeah, this is actually centimeters, it's not millimeters. And this, since it's always nicer to see some pictures of experiment, unfortunately I don't have video with me, but this is already reasonably good if you do like in feed forward. Still you are understanding the kinematics of the robot, so but you see there is especially for large deformation when the modeling error starts to be more important. You have some error here and here, but when you close the loop at the kinematic level with the IMU's estimation, you get this very nice performance here. Okay, so this is all. Just to summarize, in this paper, we did the first step toward seeing how IMU could be used in a soft robot, and we provide a general framework to do that by relying on the understanding on the robot kinematics, and we show that this actually helps experimentally when you want to do some control, like tip tracking control. And future work, we are working nowadays on two directions. One on a system level. I mean, we build this system as a kind of ideal testing setup, but we realize that it's actually quite cool in the sense that it can extend really a lot. So we're thinking, we are now working on making it more like the hardware more stable and stacking more of this segment one of the other, so to have really robot that can extend for many meters. And also it's nice that it's actuated with electric motors, not so common with soft robots. And on algorithmic level, we are working on closing the loop. So from the estimation with the projection that you have internally to our algorithm back to the Mahoney filter to reduce even more the drifting, the residual drifting that you have in the Mahoney filter. Thanks for the attention.
Very nice. Questions? Oh yes, there is one in the middle. And I'd like to invite all the other presenters to come up by the
very
stage.
very great presentation. Thank you. And my question is that you use IMU to estimate the orientation of your effector, but if you have different arc lengths, can you use this method to estimate the pose of the estimation at different situation?
So what do you mean? So actually in this, what happens?
For example, when you are changing your arc length, you still keep the same orientation. You will have a different curvature, right?
Yeah. So we have we use the estimation from the Mahoney filter to know the relative rotations, and then we look for the better explanation in terms of bending that explains that relative rotations.
So you're not just using the IMU itself?
I'm using IMU and the IMU are used to estimate rotations, and then relative rotations are used to estimate the full shape of the robot. So in the end, in the video that you have seen, this is like for example, this one is a bit small. Let me see. So in this video here, we are estimating. We have just 3 IMUs, one here, one here, one here. We don't integrate accelerometers because to get position, because otherwise it will drift very quickly. Instead, we use relative rotation, and then we estimate the shape by understanding of how the bending tends to happen. So in the end, you have a description of all the positions along the. I mean, we are showing here the backbone of the robot, but it's actually the whole volume of the system.
Okay, thank you.
Thank you.
Thank you again, Cosimo. Take a seat. And so we'll just wrap up this session on perception, which has been really, perception, as we know, is really, spanning all the, as was discussed yesterday, robotic system is naturally a multi-layer system, and you can handle perception at different levels. So you can handle perception at the planning level, and you can handle perception at the control level. So I'd like to ask the presenters, as well as Davide, who is connected online, what is the, where are the challenges? Where do you think, just because more and more sensing technology is being introduced, and advanced sensing technology in perception systems for robots. So where do you think, just putting this in perspective, where do you think will be the next challenges? Because most of, well, I would say some of the technology drawbacks or challenges have been solved, because compared to what it was like 5-10 years ago. So where are we going, and what will be the impact of integrating advanced perception systems into let me say, like intelligent robots? So this is also related to the last session of yesterday about machine learning and AI. So where are the challenges in your opinion? Anyone can start, including Davide.
Yeah, I just wanted to say that, so I think we got like a little bit too inspired maybe by the computer vision community, because I think there are just some things that are just ambiguous and can only be solved if the robot physically interacts with the environment. Like if you have like a black bag or some t-shirt and drop it on the floor, you can never from vision identify the really concrete configuration of this t-shirt. It's just ambiguous. So the robot has to pick it up and see which part of the t-shirt it got. So I think like combining interaction and perception, it's of course part of perception, but doing it in an active way is like very interesting, but also very challenging, because it introduces a lot of new things that have not been looked at by the broader community of computer vision guys.
Yeah, actually, Thursday in Gozo, we will be discussing about what we have been calling since 1 year or two, the interaction technology. So it's the challenge of, if you wish, we can call physical AI, which is us, I think, which is very much us, the robotics community. Anyone?
Yeah, maybe commenting also on what we were discussing yesterday about machine learning. I think that in the perception community, you really, I mean, it's probably where deep learning is having its, I mean, it had its maximum impact. But I think it's interesting to observe how this impact is mostly in those sensing modalities that are very related to human experience, like, for example, experience that is a bottle and that is a computer. While if you can, and it's also very much connected of not being able to define in terms of first principle what this experience means. But when we move in realms in which things are physically there, I mean velocities, distances, and stuff that you can describe using physics actually, and not depending on our personal experience. Yeah, I think it's dangerous to think that since this is all perception, the big advantage that we have on one side can be translated one-to-one to the other. I don't know if someone of you more on the deep learning side can comment.
Yeah, I think that's a good point. So, yeah, perception relies a lot more on deep learning today. And, well, when we're in the lab, we know something's going to work on the data set we have. But for robotics, when we're going to start deploying these things in the real world, in situations where not really sure what they're going to look like. There's always a domain shift, and it would be it's unclear right now how we would be able to use these deep learning solutions safely and in a way we're sure they're going to keep working properly in the real world. So yeah, maybe keeping classical approaches involved would be a solution for that. Having explainable models would be another. But yeah, I think just the domain shift that will occur in deployment of all these things we're developing with deep learning in the perception modules will be an issue.
Yeah, I'm also on the same opinion like Fabian. I think that interaction is very important because, as we discussed before, the big advances in vision have been with these deep learning models, and well, most of them are just passive, right? Work with RGB images, and actually for robotics, we also need to consider several modalities. Sensors. So if you want to have a robot doing useful stuff, I think just having one single RGB camera is not enough. So depending on the application, you might need to have depth information or tactile information. For example, you want to estimate maybe some object properties like mass or stiffness and so on. So I think there is still very much work to do to go from this like passive detection segmentation systems to systems that have a better like world model of embodied AI, basically.
And my opinion on your question is, I would agree with you. It's still in many cases super hard to go from a lab setting to the real world where you have many unexpected scenes, and I think probably for many upcoming years, this will be one of the major challenges, to really go outside and experience unseen environments and still be able to perceive them and really to represent them somehow.
Davide, what do you think quantum computing will add to the challenge?
The way, for example, we try to address such problems were the way was we try to imagine how it is to like create like a really small cell, let's say, that retains properties that we can actually find in humans that are being observed in cognitive sciences, and this kind of like architecture, human-like architecture, at least like at a perception level, could then maybe help to shape like a better way, like to help to model like a more human-like perception in that way. So that in that case, it's kind of a way to use not biologically inspired perception, but more cognition, science-inspired perception. But in my opinion, if I can add to what we were saying before, I think the great link that we have to build is like to try to shape perception and affordance by the ambience, like in order to avoid like lab settings that then are not like compliant to the real world application. So in order to like link actually how the information is processed by the robot, by the perception algorithm, directly like learn by doing, or maybe like learn by like being situated in an ambience in order to like develop affordances with the environment, rather than build before something that should work in a certain way. And that was kind of like was the idea of putting quantum computing in it in order to deal with uncertainty. And there is also some really interesting quantum reinforcement learning research right now, but it's a pretty huge field.
We'll see. Okay, I think we can close the session now, and there is a coffee break. And I propose that we start at 11:05, so 50 minutes coffee break. Okay, thanks.